Swayam Prabha. Digital India. Educated India.
Let us move on to the next problem. So this question was asked in December 2015. The major product A and B in the following reaction sequence are: an alpha beta unsaturated carbonyl compound is given. This is subjected to reaction with semi-carbazide. So that is the first reaction that gives an intermediate A. This intermediate is then further treated with potassium tertiary butoxide in diglyme, followed by heating with the tertiary butanol, leads to a product B. So these are all the two intermediates A and B that are formed in the reaction. So if you look at the semi-carbazide, a reaction of a semi-carbazide with the carbonyl compound gives semi-carbazone. And basically when we do the Wolff-Kishner reduction, either hydrazine or hydrazone or semi-carbazone is getting converted to the reduced product. That carbonyl group is, that CO oxygen is completely lost during the reduction process. So that is the one which is happening here. And when we use semi-carbazide, our expected product is semi-carbazone. And if you look at all the product, some of them are between these two things. The main difference is this is the amide nitrogen and this is the amine nitrogen. So that is the major thing we have to actually look for, because if you simply look at the NH2 group, then the NH2 group is the one that is going to react with the carbonyl group to give the semi-carbazone. That is the basic thing. But the amide nitrogen will not undergo that reaction. So we have to keep that in mind while we are solving the problem. So if that is the case, we can easily rule out some of the options which are not going to be the product. The first one is, when we do the reduction, the second step reduction, the carbonyl group has to be lost. So if you look at the product in the case of 1, 2 and 3, all of them do not have a carbonyl group, but 4 has a carbonyl group. So that means this is completely ruled out. This cannot be the product in our reaction, so that we can rule out. So now we are only left with the 3 possibilities, and out of the 3 possibilities, which one we can further eliminate is simply because we have to look at whether the reaction is shown in the amide nitrogen or in the amino nitrogen. So if you look at in the first case, this is the amide nitrogen, so this is ruled out. And in the second case again, this is also the amide nitrogen, so that is also ruled out. So finally, what is going to be the right product? We have to have only the amino nitrogen. So the question was even much simpler here, because we have 2 products in which the amide nitrogen actually undergoes the reaction, which is not the case. So that means we can easily rule out all the possibilities, and without even looking at what is the mechanism or how the reaction proceeds, we can simply say this is going to be the final product. But then let us confirm whether this is actually the obtained product or not by looking at the mechanism individually. So sometimes if you want to solve a problem, you can also do this permutation combination, which will work, which will not work. By that you can easily and quickly identify what is going to be the final product, and always confirm that by looking at or drawing the mechanism individually, so that it helps confirm that yeah, you are absolutely right with your final product. Because there are many cases, some exceptions are always there in many reactions, and we have to actually look for, say for example, a couple of examples I'll tell you. We will also be looking at some of them. If you look at the Swern oxidation, the Swern oxidation actually requires a base. If there is a base, then only the Swern oxidation happens. Swern oxidation is nothing but conversion of the alcohol, primary or secondary, to aldehyde or ketone. This happens only in the presence of a base. If there is no base, then this Swern oxidation does not take place. So this is one thing we have to be very careful in looking at what is going to be happening. And similarly, the photo excitation of the rose bengal, which we saw earlier, has to happen only in the presence of photo conditions. That is, light induced excitation is actually possible. Heat induced is not possible in this particular case. So that means if you are going to identify the conditions for a particular reaction, then you also have to look out at very specifically what are the conditions, reagents and conditions that are involved in that reaction. That will help you figure it out, what is going to be the right combination of reagents that are involved in this kind of reactions. So we have a alpha beta unsaturated system that is treated with the semicarbazide. So treating the alpha beta unsaturated system with the semicarbazide gives the semicarbazone. So as I mentioned, in the semicarbazone, we have basically, if we have to write the structure of semicarbazide, this is amide, and then you have the NH and then NH2. So this H2 and O, they both are gone as a water molecule. So we have to have the amino nitrogen is the only thing that is undergoing reaction, and it is not the amide nitrogen. So that is what you have to keep in mind while you are trying to work out the problem. So this gives the semicarbazone as our final product from the first reaction. So once we have the semicarbazone, this semicarbazone is now treated with tertiary butoxide. What is the role of a tertiary butoxide? Tertiary butoxide is a base. So what a base will do? Base will abstract the most acidic proton. So here we have this hydrogen, that is the acidic hydrogen. So the tertiary butoxide basically abstract that hydrogen to give the anion. The nitrogen anion is actually formed in this particular case. And once the nitrogen anion is formed, what is going to be the next case? This nitrogen anion actually abstracts a hydrogen atom from the solvent. So if we say this anion directly abstract the hydrogen atom, then we will actually end up with the previous semicarbazone as our final product, but the reaction may not proceed further. So what has to happen? Now it is not this amide, this anionic nitrogen that is going to abstract that alcohol's hydrogen, but it is something different, which is the double bond. In fact, what we have to say is this carbon atom that is what going to abstract that hydrogen atom from the solvent. So here we have a carbon which is having a double bond, and that double bond is now getting converted to a CN single bond. So this is what is the role of this alcohol which is involved in this particular reaction. If the anion abstract that hydrogen, because you can also ask the question, so when the anion is there, that is the most important and the most nucleophilic site which will simply pull the hydrogen atom from the alcohol. So we will actually end up with a semicarbazone as a starting material. That means, in other words, what we say is like no reaction had actually occurred. So for the reaction to proceed further, when we look at microscopic reversibility, we will also be shifting the double bonds during that whole process, so that what is the most probable one that will be formed. So this particular carbon gets the negative charge, and that is the carbon which abstracts this particular hydrogen atom from the tertiary butyl alcohol, that liberates the tertiary butoxide anion. Okay, so this tertiary butoxide anion is liberated. And once the tertiary butoxide anion is liberated, what will happen is like this tertiary butoxide anion is going to attack the amide carbonyl, because this is the electrophilic site. This electrophilic site is being attacked by the nucleophilic base, and then shift of bonds actually takes place. The carbon nitrogen bond is actually broken to give the N2 gas, because when this breaks, we end up with the nitrogen-nitrogen triple bond will be formed. Similarly, the other carbon-nitrogen bond is also broken towards the carbon atom. So when this happens, what are all the products that will be formed is we end up with the carbanion as well as the loss of nitrogen atom. So the loss of nitrogen atom is the driving force for this particular transformation to take place. Once we have the anion, you obviously know there is an alcohol, that is a solvent that is present. The anion will abstract the hydrogen atom from the solvent, and it gets neutralized to give the saturated, that is the carbonyl group is actually reduced in this particular case to give the reduced product as the final one. And this modification, this is basically the modification of Wolff-Kishner reduction. Wolff-Kishner reduction basically uses semicarbazide or hydrazine to convert a carbonyl group into the methylenic compound. And in this reaction, there is also another mechanism some people had proposed, that the semicarbazone can also be getting converted to directly to the hydrazone. So that is also possible. So in that case, what will happen is like, this is very similar to the loss of this amide group actually happens. Okay, when this particular amide group happens, we end up with only this unit. This unit is nothing but, because here we end up with a hydrogen. So when we have the NH2 unit here and this nitrogen is attached here to the double bond through this bicyclic system, that is nothing but the hydrazone that is formed in this reaction. So once the hydrazone is formed, this will also follow the same type of reaction. So that here also the same thing, like loss of hydrogen atom, that is the abstraction of the first hydrogen atom leading to the formation of the anion, and then loss of nitrogen gas giving the carbanion, the carbanion abstracting the hydrogen atom from the solvent to give the reduced product. So these are all the same set of sequence of reaction will also proceed from the hydrazone derivative. So people had proposed two types of mechanisms: the semicarbazone directly undergoing the reaction, or the semicarbazone getting converted to hydrazone and then hydrogen undergoing the same set of reaction. So both probabilities are possible, and this is basically called as the Henn-Best modification of Wolff-Keshner reduction. So let us move on to the next problem. So here again, the major product A and B formed in the following sequence of reactions. So here, this question was asked in December 2015. We have a carbonyl unit, and this carbonyl unit is subjected to various reactions. We have actually multiple reactions are happening. The first one is in the presence of a strong base, sodium tertiary butoxide, that is 2.2 equivalents, and 2.5 equivalent of methyl iodide are used in the first step. So if you look at these two things, you have a base, you have an alkylating agent. So obviously what is the reaction that is going to happen is alkylation reaction. So this is the first step, and then it is followed by sodium borohydride and methanol. So after the alkylation is over, then what we are doing is the reduction of a carbonyl group, because sodium borohydride is generally used for the reduction of the carbonyl group. So that will happen. So that means we may end up with an alcoholic product. Then the third one is reaction with acetyl chloride and pyridine. So this is nothing but the acetylation of the alcoholic unit that is formed in the previous step. And the next step is reaction with the trifluoroacetic acid and triethylsilane, because this is a new reagent we will be looking at in the presence of DCM. So the triethylsilane is generally used for the reduction reaction. We will have to see what type of reduction and how the reaction mechanism, those things we will see a little bit later. But one thing we have to remember, the triethylsilane is generally used for reduction reactions, or sometimes deacetylation. In this particular case, we can when we look at the mechanism, we will find it out. It is basically the deacetylation reaction in which this is actually involved. And then we end up with some intermediate A, and this intermediate A is further subjected to lithium in liquid ammonia, that is nothing but the birth reduction conditions in the presence of tertiary butanol as a solvent, and the reaction happens at minus 40 degrees centigrade. So we are generally probably going to end up with the reduction of this aromatic system. So that is what is going to happen in the second conversion from A to B. So the final product B, what it can have is, we are going to look at what are all the different products that is possible. So the first one has the aromatic unit intact. So that means when we carry out the bridge reduction on an aromatic system, the aromatic double bonds, one of the double bond is going to get reduced. So that means we are not going to get this product. So 1 is ruled out, and 3 is also ruled out because this is also phenol. So that means 1 and 3 are not going to be the so if we look at B, so this one is having the phenol, so this is completely ruled out, and this one is possible. When we move to the next one, we have the aromatic ring that is reduced. So the only difference is where is the double bond, whether it is on the methoxycarbon or it is not on the methoxycarbon. So that is the major difference we are going to look at, and based on the electron donating nature of the methoxy group, we can easily predict what is going to be the right product. And similarly, we have a carbonyl group that is formed, because birth reduction may not give the carbonyl group. So that means this is also ruled out. So in other words, we can completely rule out 1 and 3, and we have to only look at either the final product is going to be 2 or 4. That is the only thing. And if you look at A in both the cases are one and the same. In other words, if it is going to be the alkylation followed by reduction and then acetylation and reaction with triethylsilane, all of them will reduce the carbonyl group. So that is what actually happening in these two cases with alkylation happening simultaneously. So 2 and 4 could be the product, and the only thing differentiating factor is whether the Birch reduction will give when the double bonds are reduced, whether the double bond will remain on the methoxy carbon or not on the methoxy carbon is going to be the deciding factor for identifying our product. So this is the quickly, without doing any mechanism and other thing, we are going to identify what could be the final products. Let us look at the mechanism elaborately, find out how the reactions are actually happening. So the first step is the alkylation reaction. So when we use two equivalents of methyl iodide, so this alpha carbon is the most, has two acidic protons, and these two acidic hydrogen atoms are removed by the base, and the nucleophile attacks basically the methyl iodide. So the methyl group attacks these places and we end up with the alkylation that is happening here. So we get the dimethyl product as the first reaction product, and this is further subjected to reaction with the sodium borohydrate. So sodium borohydrate reaction is nothing but the reduction of the carbonyl group. So here we have the carbonyl group. So that carbonyl group is reduced to the corresponding hydroxy unit. So the reduction of the hydroxy unit takes place as the second reaction. And the third reaction is reaction with acetyl chloride and pyridine. So this acetyl chloride pyridine reaction is nothing but the acetylation of acylation or acylation of the alcohol unit. So this is the introduction of the acetyl unit or the acyl unit on the hydroxy is happening. So this is the next reaction. So it is followed by two individual steps. First one is treatment with the trifluoroacetic acid. So when we use a trifluoroacetic acid, what happens is basically the reaction is having plenty of protons. So the proton source is high, and oxygen pulls the electron towards itself, so that we end up with the corresponding hydroxy unit like this, and we have the oxonium ion that is present here. So under the influence of the carboxylic acid, we end up with the oxonium ion that is shown as shown here, and this is now subjected to triethylsilane reduction. So when the triethylsilane reduction, that is nothing but the hydrogenolysis of the acetyl unit, so the silane's hydrogen atom is transferred to this particular carbon atom with the concomitant loss, because the oxygen is having the negative positive charge, oxonium ion. So this is quite unstable. So the carbon oxygen bond is now broken towards the oxygen, and we end up with the CH3COO is nothing but the acetic acid is formed as the byproduct, and this particular carbon is reduced. So this is our first intermediate. So here we have the dimethyl, gem dimethyl group are introduced through the alkylation reaction, and the carbonyl group's CO is reduced through the various steps, conversion of the carbonyl to an alcohol, alcohol to acetyl, acetyl to deacetylation, leading to the reduction of the complete carbonyl group. That is what is happening here. So up to here we have carried out all the reactions, and finally we are going to look at the final thing, which is the Birch reduction conditions. So Birch reduction reduces the aromatic system. So here the most important thing we have to remember is the methoxy group is on the double bond, because whenever we have an electron donating group, they always are present on the double bond. When it is electron withdrawing group, they are away from the double bond. So that is what is the product, final product that will be formed in a Birch reduction. So in this particular case also, we can actually look at the methoxy group is present on that. So based on that, we can actually say what is going to be the final product. Even though the reaction looks very lengthy, all these reactions are very simple transformations, and we can easily follow through how each steps are being carried out, and then finally we can easily identify what is the product. So the only new reagent which is not common in this particular case is the triethylsilane reducing agent that is used in the hydrogenolysis of the acetyl unit. Let us move on to the next problem. So this problem was asked in June 2017. The major product formed in the following reaction sequences are. So there is a Para-methoxybenzyl ether, PMB ether, this is generally called as para-methoxybenzyl ether, is given here, and this is subjected to reaction with the DDQ, and we end up with a product or intermediate A, and this intermediate is now treated with phenyl iodoacetate and followed by reaction in the presence of a solvent methanol to give a product B. So these are all the two sequence of reactions that is happening, and we have to identify what is A and B. So as I mentioned, para-methoxybenzyl ether is a protecting group for alcohols. So that can be easily cleaved very specifically by DDQ. So our first intermediate is nothing but the cleavage of this particular bond. So that is what is basically happening here. So then if you look at the final product, we have 1, 2 and 3. All of them have the deprotected one. The third one has the para-methoxybenzyl unit. So this is not the product, we can completely ruled out. So now what is going to be the next one? We are going to see the reaction with PHI OAC2, that is phenyl iodinium acetate, is the one that is going to convert this corresponding alcohol to some other product. So if you look at various cases, we have the carbonyl group that is formed. In another case, we have a carbonyl group with methoxy is present in the system, and another case we don't have a conversion. That is again, if you look at 3, in the 3 we actually have the aromatic ring, the one of the cyclohexyl system is converted into aromatic system. So this does not even happen. So we can also rule out this one. So we now have only 2 products that are possible, either 1 or 2. And in one, the methoxy unit is present in the cyclic system, and in the other one, the methoxy is present in the ring junction. So these are all the 2 products. Now we have to find it out by writing the mechanism. But if you look at all the other cases, in one of the cases the double bond is in the second system. In the other other option, we have the double bond is not present in the second system. So these are all the only 2 changes. Now we have to, by looking at the mechanism, we are going to identify what is going to be the product. So we can easily rule out the product. Option 3 and 4 are not the product. Only we will have to look at either 1 or 2, which is going to be the right product. So here is the reaction. We will look at how the DDQ cleaves that double bond. The para-methoxybenzyl ether is cleaved by DDQ. We are going to see. So the entire name of the DDQ is given here. This is 2,3-dichloro, 5,6-diazono, 1,4-benzoquinone. So this benzoquinone unit is the most important thing we have to keep in mind, because this is very crucial for the reaction, how it proceeds. This DDQ basically facilitates a single electron transfer, and we have the methoxy ether, that is the starting material that is given. We have simply put the R group for the alcohol, and the rest of the thing is actually given here. And when this undergoes a single electron transfer, so one electron is being transferred here, and we end up with a radical cation that is formed here, as shown in this particular case. Because one radical is actually transferred to this particular carbon, because of the methoxy group's presence, this particular carbon is carbon takes that radical, that is a single electron that is being transferred from DDQ, is taken by this particular carbon, and then obviously the double bond, one of the double bond shifts, that leads to the formation of the carbocation on the other opposite, that is the para position carbon has the carbocation. So combination of the carbocation and the radical present on the same system is called as the radical cation. So this is the first intermediate that may be formed. So this intermediate loses a proton, because the carbocation carbon is quite unstable. So we have a neighboring hydrogen which can be lost as a proton. So this is basically lost as a H proton is lost here, and we have a double bond that is formed between these 2 carbon atoms. So this is nothing but the radical. So this radical, as you know, are highly reactive species. So when this radical undergoes CC coupling reaction, so that is it will again undergo one more single electron transfer. So during that process, we end up with a positive charge on the methoxy group. So here, one electron is added here, and the lone pair of electron is also involved here. So we end up with this intermediate is formed, which is the oxonium ion that is formed in this particular case after the single electron transfer, and this undergoes reaction with water molecule. So we have a electrophilic carbon which is highly present here because we have a oxonium ion here. So this will pull the electron towards itself, and this will have to shift towards the here, and this will shift here. So in other words, this carbon becomes delta positive. In other words, this is going to be the most electropositive carbon in that entire molecule. So we have a electropositive carbon, and we have a water molecule which has lone pair of electrons. So this lone pair of electron attacks this carbon. So we end up with the water molecule that is getting inserted. But when the water molecule is getting inserted, we actually have a plus charge, and this plus charge will be neutralized by the loss of this proton. So we end up with the hydroxy derivative that is drawn here directly. So during the whole process, as the shift of bond actually takes place, we end up with the methoxy group losing the positive charge. In other words, the positive charge is neutralized by pulling that pi electron towards the oxygen atom, and this molecule has two oxygen units on the same carbon. So this is quite unstable. So this will lose the OR group. The alkoxide anion will be lost during the charge reversal process, because what happens is, like, this one of the bond is shifted towards here, and this will come out towards the alkoxide anion. So we end up with the aldehydic unit as the byproduct, and we have the alcohol, because in other words, we started off with the para-methoxy benzyl protected alcohol was used as the starting material, which lost this RO bond. This is broken to give the alcohol that is formed as the final product. In other words, the protecting group of the para-methoxy benzyl ether is cleaved by the reaction with DDQ. So this is how the whole process takes place. In other words, we can do the same thing for our alcohol. So this is our starting material. So this starting material has the para-methoxy benzyl ether unit. When treated with DDQ, undergoes cleavage to give, or deprotection to give, the corresponding alcohol unit. So what is the driving force for this reaction? Basically, the presence of the methoxy group is the stabilizing factor. This stabilizes the intermediate, the radical cations, and the other species are basically stabilized by this para-methoxy group. So that is one. And in the second case, we also have the DDQ is actually the non-aromatic system, which is getting converted to an aromatic system. So these are all the two driving forces for this particular reaction to proceed. So once we have this alcohol, the next one is the iodine 3 carboxylates reacts with this corresponding phenol unit, and we end up with the aryl lambda 3 indane. So this is the intermediate that will be formed in the first step, and this is then reacted, because this undergoes attack from the solvent molecule, because if you look at the solvent that is used, that's a methanol that is used. So this has a lone pair of electrons. So this attacks this bridgehead carbon atom. By the shift of bonds actually takes place, and this leads to a radical cation intermediate, and this then loses 2 electrons and 2 protons to give the corresponding derivative as shown here. So we end up with, because the methoxy unit attacks the bridgehead carbon, so that is where the bicyclic ring, the ring junction is the place where the methoxy unit is actually attached. So our final product is going to be the methoxy unit in the ring junction. So this way we can easily identify what is going to be the final product, because the other one has the double bond here and the methoxy unit here, so that is not the product, but the methoxy unit at the ring junction is our final product. So that way we can actually identify what is the final product in this reaction. So basically this iodine 3 center is reduced after the reaction is over, and we end up with the dienone. So this is the final product that is happening. So the overall process of conversion of this radical cation intermediate to the final product occurs through the loss of 2 electrons and 2 protons. So let us move on to the next problem. So this question was asked in December 2011. The major product A and B in the following reaction sequences are: we have cyclohexanone as the starting material. Phenyl magnesium bromide is treated in the first step. The next, it is also treated with paratoluene sulfonic acid. We end up with an intermediate A. This intermediate A is further treated with borane dimethyl sulfide complex in step 1, followed by pyridinium chlorochromate in the step 2, and metachloroperoxybenzoic acid in step 3. So 3 steps are carried out and we finally end up with the product B. So these are all the 2 sequence of reaction that is happening. As we know, phenyl magnesium bromide reaction generally leads to the formation of a Grignard. This is nothing but the Grignard reaction. So Grignard reaction on a carbonyl compound leads to a alcohol. So that is the obvious reaction we all know. And treatment with paratoluene sulfonic acid of this alcohol basically leads to dehydration. So these are all the first 2 reactions that is happening. So then we end up with the intermediate A. So let us look at what are all the products that are having the alkene unit.
If you look at the first option, the 2 steps Grignard reaction and the elimination gives the cyclohexane derivative. Here this is the intermediate A. This intermediate A when undergoes the next 3 reactions to give the lactone. So the option 1 may be possible.
And if you look at the other product, the second one is we are having the hydroxy group. That means alcohol is formed. But then treatment with paratoluene sulfonic acid will facilitate a dehydration reaction. So that means the alcohol cannot be present. So this is ruled out. So we don't have to look at the other product what it is. So by looking at the first intermediate itself, we can rule out possibilities in this reaction. So now we are left out with only 2 things. If you look at the structure of 3 and 4, that is the intermediate A, in both the cases, they are one and the same. So that means they both could be the product. We have to identify now. We have to move to the second one, B, to identify what is going to be the final product. If you look at the reagents that are used, the first one is the borane dimethyl sulfide. Borane dimethyl sulfide is generally used for hydroboration reaction. So that means the alkene will be getting converted to an alcohol. PCC is used for the conversion of an alcohol to either aldehyde or ketone. So that means the formed alcohol from the hydroboration reaction will be oxidized. So we may end up with a carbonyl compound. And when we have a carbonyl compound, MCPBA reaction basically leads to Baeyer-Villiger oxidation. In other words, a carbonyl group when treated with metachloroperoxybenzoic acid will be converted to a ester. Okay, if it is a cyclic one, it will give a lactone. If it is an open chain, it is going to give ester. So in other words, if you look at 3 and 4, 3 is basically the carbonyl compound. So that means if MCPBA undergoes, if MCPBA is used for the reaction on this particular ketone, we cannot have a ketone as our final product. So what we can say, 3 is also ruled out. So that means 4 is again an epoxide. So now we have to see what it is, what is the product we are going to actually have. So let us look at the reaction. So the first reaction is nothing but the Grignard reaction. The carbonyl group is reacted with phenyl magnesium bromide. We end up with the corresponding tertiary alcohol. So conversion of a cyclic ketone to a tertiary alcohol is the first step that is happening. And in the second step, we are treating the elimination reaction. So if you look at how the reaction actually proceeds, the alcohol is treated with the paratoluene sulfonic acid. So this hydroxy alcohol has lone pair of electrons. So the lone pair of electron abstracts that hydrogen atom with the OH bond getting broken towards the paratoluene sulfonate anion will be formed in this particular case, because this has multiple double bonds. So in other words, a charge, a negative charge on this oxide anion is highly stabilized by the neighboring sulfur containing oxygen units. So this resonance stabilization is a crucial thing. That is the reason para-toluene sulfonic acid can easily donate that hydrogen atom to the the alcohol. So we have a hydronium ion that is formed as the intermediate, and this hydronium ion, as you know, is quite unstable species. So this will immediately go away as the by the loss of water molecule. So we end up with a carbocation. So when we have a carbocation, we have a phenyl group in the neighboring unit. So the phenyl group can actually stabilize this carbocation. In other words, this carbocation will be formed very quickly. And once the carbocation is formed, because it's again is a intermediate, which is a unstable intermediate, we have a hydrogen atom in the neighboring carbon, which can be easily lost. So that leads to the formation of alkene. So this is our next product that will be formed in the dehydration reaction. So the PTSA's dehydration leads to the alkene as shown here. So here this is this reaction proceeds via even mechanism, that is the carbocation is involved in this reaction, and the product that formed is the Zaitsev product or the more substituted product. And the next step, as we move forward, the alkene is now treated with the borane dimethyl sulfide complex. So how this reaction actually proceeds? This is basically a hydroboration reduction reaction leading to the formation or conversion of the double bond alkene to an alcohol. So the alkene reacts with the borane in the first step. So we have a four-membered cyclic transition state as shown here, and boron is having the negative delta negative charge, and this one of the carbon, alkene carbon, is having the delta positive charge. So based on that only, in this particular case, the addition of boron takes place, because boron can also add from the other side. The boron here with the two hydrogen atoms and another hydride here. This way also we can have a possibility of the addition, but this carbon can better stabilize the positive charge. So that is the reason after the charge polarization, this carbocation having a delta positive charge on this most substituted carbon is easily stabilized by the plus psi effect of the alkyl groups that are present here. So that is the reason the boron adds to the next carbon, and that leads to the finally this is 3 units of the alkene can be added to the boron unit, because the boron has 3 hydrogen atoms. So this is the first unit that is added from the alkene. So this hydrogen can also be replaced by the second alkene. This also can be replaced by the another alkene. So 3 alkene unit can replace all the 3 hydrogen atoms of the boron to give the boronate ester as shown here, and this is further reduced to give the corresponding alcohol unit, and this reaction follows anti-Markovnikov addition. So we started from the carbonyl compound that is getting converted to the corresponding tertiary alcohol that undergoes dehydration to give the alkene. The alkene is getting converted to the alcohol by the hydroboration reaction. So this is now further oxidized by PCC. So the oxidation of PCC follows as the mechanism is shown here. We have a alcohol unit, and this is the pyridinium chlorochromate. So the pyridine is having the positive charge, and the oxygen, one of the oxygen that is attached to the chromium, is having the negative charge. So we have a negative charge here. In other words, the chromium is having the positive charge. Delta plus will be there. So the lone pair from the oxygen attacks this particular oxygen on the chromium with the concomitant shift of one of the bond towards the electronegative oxygen atom. So this intermediate is formed, but as we know, we have a very good leaving group and we have a negative charge nearby. So this negative charge comes here and this is lost. So that way the concomitant movement of electrons takes place by loss of Cl minus ion. So we end up with this corresponding chromic acid type derivative, and this one further undergoes loss of this hydrogen atom, because this is quite an unstable intermediate. So this hydrogen atoms bond shift towards this oxygen with this bond going towards the chromium. So we end up with the corresponding chromic acid as a byproduct, and the carbonyl compound is actually formed. So this way an alcohol is getting converted to the corresponding carbonyl compound. If it is a hydrogen atom, then we are going to end up with the aldehyde. If it is a R group, then it's a secondary alcohol getting converted to ketone. So this is how the chromyl chloride PCC, pyridinium chlorochromates oxidation takes place. So we end up, that is the conversion of the secondary alcohol to the ketone takes place, and then finally this is subjected to Baeyer-Villiger oxidation. So when this carbonyl compound is subjected to Baeyer-Villiger oxidation, we end up with a, this is a cyclic ketone, so we end up with a lactone derivative, and here the migration of the group that actually takes place. So any substituent that can stabilize the positive charge that migrates. So one thing is like, I mean, this carbon can migrate or this carbon can migrate. So based on that, this particular carbon migrates between the carbon and oxygen. So the oxygen is inserted here. So we had earlier seen what is the Baeyer-Villiger oxidation's mechanism. So this particular carbon actually shifts towards this oxygen. The another oxygen will be coming here from the peroxybenzoic acid. So this will now shift towards here, and that is how the shift of, because this is having the most this particular carbon's positive charge can be easily stabilized because of the presence of the phenyl group. So this is the migrating carbon, and it is not the other carbon, because this carbon now cannot migrate to this oxygen because this is not stabilized compared to this particular carbon. The positive charge on this carbon is highly stabilized. So we end up with the group that can actually stabilize, the migration takes place on that particular carbon which is actually stabilized. So this stabilized carbon shifts to give the corresponding lactone derivative. So this is the first intermediate that is formed, the alkene, and the final product is basically the lactone. So these are all the overall reactions that is happening here. Let us move on to the next problem. So this problem was asked in December 2011. The major product A and B formed in the following reaction sequence are. So here we have the aromatic compound that is given here. It has a methyl group and a methoxy group. This is treated with the lithium and liquid ammonia in the presence of tertiary butyl alcohol. This is nothing but the Birch reduction. We end up with the compound A, and this compound A is treated with the MCPBA. So what is the product that is going to be formed, that is what we are going to see. So we have seen earlier also, when we have a electron donating group, the Birch reduction gives the double bond on the electron donating group. So if we extend the same for all the cases 1, 2, 3, 4, so this one has the methoxy group on the double bond. Here again the methoxy group on the double bond. Here again methoxy group on the double bond. Here it is not on the double bond. So we can rule out this is not the probability. So we have 3 other products that are possible. And again here also, if you look at these 2 cases, we have the methyl group. This is also partially electron donating. So in other words, this is not the possibility, and only these 2 and 3 are the most probable thing that may be possible. And in this particular case, MCPBA generally epoxidizes the alkenic double bond. So we have a epoxide that is formed on this carbon which is attached to the methoxy unit, and in the other case the epoxide happens on the methyl substituted carbon. So if you look at these 2 things, methoxy is more electron donating compared to methyl. So in other words, what we can say is this may probably be the expected product in our case. So that is how we can easily identify, without looking at the complete mechanism, what is going to be the probable product. Let us confirm this using working out by the mechanism. So if you do the Birch reduction, as I mentioned, the Birch reduction gives the 1,4-diene, and when the 1,4-diene is formed, both the electron donating groups are on the alkenic carbon. So this is the first intermediate that will be formed in the Birch reduction condition. And once this is formed, what is the next step? Next step is nothing but the epoxidation. So how the epoxidation actually takes place? in the solution, what happens is like we have 3 oxygen atoms are there. Although oxygen is electronegative, but in this particular peroxy acid, what happens is one of the oxygen is actually having the delta plus charge. In other words, one of the oxygen is electropositive in nature. Because of the presence of that electropositive oxygen in peroxy acid, that undergoes epoxidation reactions very effectively with the nucleophilic or the electron rich pi bonds. So that is the reason alkene epoxidation is highly facilitated by peroxy acid and not by normal acids, because normal acid also has 2 oxygen atoms, peroxy acid has 3 oxygen atoms. So what is the difference between peroxy acid and an acid? Simply because in the peroxy acid we have an oxygen which is electrophilic in nature because of the charge polarization between that. If you look at this particular bond, this bond is actually polarized towards oxygen. That is very easy. We can easily say that. Now, this is going to be a delta plus charge on this particular carbon atom. But if you look at the other 2 oxygen, the other 2 oxygen can actually polarize towards any direction. If this oxygen gets polarized as a delta plus charge, then we have 2 Coulombic interactions or a Coulombic repulsion that is happening, because you will have a carbonyl carbon having a delta plus charge and you are also having an oxygen having a delta plus charge. So both of them will repel each other. So in other words, those kind of polarization is not feasible. So what is the other way possible? Now this oxygen can have a negative charge, we have a delta plus charge, so these 2 are attracted towards each other and we have a oxygen that is having the electropositive charge away from the electrophilic carbon atom. So in other words, this type of polarizations are possible in solution, and this is what is very, very crucial for the epoxidation reactions of alkenes. So once we have a nucleophilic double bond, in other words electron rich double bond, we have a electrophilic oxygen. So there is a bonding that occurs here, and in fact during the whole process there is a weak hydrogen bond that also exists between the oxygen, the carboxylic acid's oxygen and the hydrogen atom that is present in the acidic peroxy acid. So this is also a stabilizing factor in the case of peroxy acids in solution. So once the shift of bond takes place as shown here, we have a transition state, and this transition state looks like a butterfly. So people call this as a butterfly transition state, and this butterfly transition state transfers the oxygen atom to the olefinic bond, thereby giving the epoxide unit, and we end up with a carboxylic acid as a byproduct in this case. So when this transfer of oxygen takes place, it takes place from the same side. In other words, we say there is a cis epoxide that is formed in this case, and based on that we have to look at what is the alkenic bond that is electron rich in nature. So even though we have that epoxidation takes place on both alkenic bonds are possible, since this has a methoxy unit which is electron donating in nature, so this double bond is even more nucleophilic or electron rich in nature, so that undergoes the epoxidation very effectively compared to the other group where the methyl is one of the substituent. So this type of epoxidation is called as Priledshev reaction or metachloroperoxybenzoic acid facilitated epoxidation of alkane. So this is how we can easily find it out what is the final product formed in this particular reaction.